welcome back Mohammed Ghidaoui. Mohammed did his PhD here at U of T and his undergraduate degrees too. He graduated from here in 1993.
Yeah, PhD in 93.
PhD in 1993.
Civ 89.
Civ 89. They had a 30-year celebration, which I understand was pretty well lubricated.
Yes, suds again, suds.
Remembering things. Mohammed is currently a professor and name chair in Hong Kong at University of Science and Technology. He's also the editor of the Journal of Hydraulic Research, which is a very premier journal and won a number of awards. I've mentioned in the Civ 1303-401 class that conduits are conveyors of water and other substances, of energy, and of certainly of dollar values and economics, but they're also this marvelous conduit of information. And Mohammed's talk today is going to very much specialize in the way we can listen to a pipe system in order to extract some of its characteristics and maybe some of the places that it's going wrong as well as where it's going right. So I'm delighted to welcome you here today, Mohammed. I think you're in for a very fascinating time.
Okay, well,
Mohammed.
Thank you, Brian. I hope you'll applaud at the end as well. Well, thank you all for being here. It's certainly a pleasure to be back home. It's really home. I haven't been back in Toronto for about 24 years, but you know it's home when you arrive and you fall back in place. Everything seems familiar. There's a few buildings here and there, but really the place is still very exciting and lots of fun. Yeah, Friday night was suds, and we feel quite hard done because we used to close shop at 7. Now it goes on till 11. So it's nice to be back. In any case, everybody can hear me, all right? Yeah. So the talk today, it's time reversal. I'll go through. There will be a few videos to kind of get the idea first, kind of through, and then we will see how we use it, how we apply it. Now, I like to start with this. Now, how do I start the video?
Yeah. Just click on it now.
Yeah. So often when time reversal ideas or you hear the notion, it's things like this that come to mind. Maybe not a glass of wine, at least to me it does. For you, whatever, but very immediately people would think it cannot happen. And I will share with you later why that's very unlikely to happen. Actually, it could happen, but the probability of it is infinitesimal. It so happens that with waves, as I will show you, they're actually very robust. With waves, they can retrace their path in time very, very well. So the idea is this, is if you have a sound source, a point source, for example, you might have any inhomogeneity in the system. You start a wave, and we are all familiar with these ripples that kind of emanate from the point. And what you could do is measure, for example, the pressure at a couple of locations. And the idea of time reversal is you take what you measure here and essentially switch it in chronological order. So LIFO, last in, first out. And you send it back. And what you will see, a few experiments, I'll show you videos, is that all of these waves will retrace their path and converge back on their point of origin, and only to their point of origin. And where we use it later is actually then defects, like leaks, for example, are nothing but sources of waves. So that means waves can find them. Waves can find any of these defects. So that's the way in which we use it. Now, there is one thing that you will see me referring to later. When these waves converge, if they start from a point, they can only converge to within one wavelength over a half. And that's what's called the diffraction limit. So they cannot go back to a point, they can only go back to the wavelength over a half. So if you want better focus, you need a shorter wavelength. Means you need higher frequency. And you will see me later saying that's why we want to go for higher frequency. Higher frequency, we localize things to a few centimeters, at least for our applications. But here is a cool video. It was actually, you can find this in the internet, but so what you'll see is a stone, and the first part of the video is simply, again, what all of us observed, and what they're going to do is measure at just a couple of places. They're going to measure the pressure at a couple of places, and so you have to bear with me. I think it runs for about 30 seconds. Then what they're going to do is take what they measure, this pressure here, and the only thing you do is run it in chronological order. Last in, first out. So now it's running back, and you will see for quite a while, really not much happening. But observe, be a little bit patient. It's cool. You should see, you should see the wave converging back and really finding its source. The only thing that's not going to basically trace is the stone. The stone is not going to come back up. And there is a reason for that. We will explain why. So it starts to kind of organize itself. Doesn't look much yet. And that's the surprising things about it. Like, looks often like you're going nowhere with this until they suddenly, and that's one of the amazing things with waves. It's worth it, so I hope you bear with me. I watched this many times. You see it? You see it? Right at that point. What you see now, you see these things is what we call side lobes later. It goes back to the point, but you still see a little bit of waves around. The reason for that is we did not measure at every point. So if you do measure at a lot of these points, then you will be able to cancel all of those waves. Either that, or if you have a closed basin like this, either you measure at every point or you measure at one point but for a long time. If you measure for a long time, every wave will eventually pass your measuring points. Okay? But if the idea is to refocus, then you already got it. That's for gravitational waves. I'll show you another video for electromagnetic waves. So electromagnetic waves are also time reversible. So what you'll see here is a source. And again, they are measuring at 4 locations. So again, the same idea. You measure at a few of these points. You time reverse it. They will. And you will see the waves refocus. So I'll show you this video, and then I'll skip a couple of the other ones to save a bit of time. So the idea again, the source was here, you're measuring the pressure. Now you take what you measure, that pressure, you time reverse it and send it back. Okay, so now again you will see the same stories. The wave will converge back at their source. They actually find their home. So it's in that sense we call it time reversible, is that the waves actually recreate their past steps. Okay, so again, bear with me, and I will not, then the next one I will skip it. It's acoustic waves. They are also time reversible. So all waves are actually time reversible. All waves, gravitational waves. Nonlinearity does not prevent them from being reversible as well. Okay, so this is acoustic, so there is a movie, I'll skip that. One of the demonstration of this was actually in Mediterranean Sea. I think it was a 30-kilometer distance where this is the source. Again, they send these waves. This is one of the early experiments they've done. They send it and they measure at a few of these locations. Again, the same idea. You take the waves, you time reverse them, and they refocus back on the source. And we are not looking large amplitude here. They are very small amplitude type waves. And for this one, there is a short video. What you will hear, they turn into sound. Oh, how come it's not playing? This is, by the way, the picture of oh, because we turned off the sound. Okay, all right. So actually what the video is, it shows you, it's a short pulse. So it shows you pulse, ding, and when they measure here, it will be elongated. There is a lots of echo, lots of reverberation. So it'll be long, they send it back, and it goes back to basically a pung. So you actually undo the echoing. This became essentially basically there's a lot of technology that came out of it. One of the technology they use is for kidney stone, to destroy kidney stone. So what they do in a kidney stone, you have the kidney stone and you have the tissue around it. you would like to put a lot of energy on the stone, and you don't want to destroy the tissue around it. So what they do is they send a test wave, a small wave. It goes and hits, of course, the tissue and the stone. The stone, of course, will send stronger reflection. So you focus on that. You just take what is reversed, what comes back from the stone, you time reverse that, and that's what they do, and they put a lot of energy. And what happens with that is that all of the energy will focus on the stone and leaves everything else untouched. And that's how they destroy kidney stone. So this is one of the applications. Recently, actually, I've been looking whether there is a lot of civil application. I'm finding there is maybe about 6, 7 papers of people starting to look at this for structural engineering application, for defect detection in plates. So one of the things they do is they send a wave at A, receive it at B, and so on. Once then you measure it again, you time reverse it, and you rediscover back the wave you send. And that's precisely what was being done here in these aluminum plates. So what they do with it, because once that's the case, all of these defects are themselves sources. So they could use that property to image these defects. Okay, so that's the imaging actually they got from it. It tells you where those cracks are. Now to our pipelines, and Barry, you will see a familiar face here. Duncan holding. So what we did here is a burst. This is in the field. So we open up the pipe here, and it sends, of course, 2 waves at about 1 kilometer per second, and we are measuring some distance away. I think it was 100 meters each way. And this is the signal we measured. We time reverse it, and we put it back in the computer, and you will see it goes back to the burst. So actually, I'll show you later that that's actually one way. If you are measuring in the field, if you see a drop in pressure, take it, send it back, it tells you where your burst is. Okay? And it's really a quick and very, very reliable way. Okay, so now you will see it run in time. So we reverse the signal. Okay, and this is the time reversed, and we are measuring here, and you will see it dropping at that location. The minimum point is at that location. Of course, it's the minimum point because that's where you opened up the pipe. That's where the pressure dropped. Now then we tried high frequency. Now I hope you already, let me remind you why we want high frequency is because we want high resolution. We want to localize. You will see that with mechanical devices, valves and so on, we could tell you where leaks and defects are within tens of meters. Lots of operators, like in Hong Kong, they say it's too expensive. So they want to have a more accurate localization. You want to have basically better focus. Better focus, you need higher frequency. Higher frequency to the point, if the frequency is high enough, if your wavelength is about the diameter of the pipe, you end up having radial waves as well. So we have waves along the pipe, waves that move radially. So they bounce up and down. Okay? So now you will see a numerical test, and then I will show you an experimental test for this. So what we do, I think here was about 20 kilohertz. With 20 kilohertz, we create actually, we send the pulse, it gets divided into 3 waves. One of them is the plane wave that goes straight along the pipe. Another one is the first mode that zigzags. And the other one is the second mode, which even zigzags more. And that's why they get separated. Okay? So essentially the plane beats them, and then the first mode second. So what you do in time reversal is essentially you send the slowest first, and the second slowest second, and the very slow last, and they catch up with one another, and they only catch up at the point of the source. So that's actually how they localize. All right, so now it's repeating itself. So now you will see it run a reverse. So this is a numerical simulation that we've done. So now notice the slow one goes first, the third mode. The plane is catching up, this is the straight one, and they meet, and they focalize at their source exactly. So we've done this in the lab, where we have a pipeline, and this is a viscoelastic pipe. We have a source here, we send a wave, we receive it. Okay, so you receive the wave, and that's the forward type of problem. Then we measure that signal, we time reverse it here, we send it back, and again, you will see that it gets the refocusing. So the top part is the forward problem. Okay, so you see again, similar to the numerical, the three waves are separating from one another, they're dispersing. Okay, we measure them at the end, and then we time reverse them. And this was when we didn't show you this in France, Brian, because we didn't have the experiments, but now we do. This was, I think, run at about 30 kilohertz. Okay, so we get these conformations. So why waves are reversible, particles are not? Why the glass of wine, when I showed it to you, it's even if I could sit here and try to convince you, you'll never agree to it, but with waves, I think you've seen it, and they're quite robust. Well, let's look at the basic physics. Basic physics is that Newton's laws for particles are time reversible. Second derivative with time, change t to minus t, nothing changes. Okay? The energy equation, change t to minus t, everything stays the same. The wave equation, at least with no damping, I'll tell you later what we do with damping, change the t to minus t, everything stays the same. Remember I said electromagnetic waves? Well, the Maxwell's equation are actually time reversible. Quantum mechanics, these are Schrödinger equations, they are time reversible, and so on. So all basic laws of physics are time reversible. So this actually led Locksmith. There was a big debate between Boltzmann and Locksmith in about 140 or so years ago, and Locksmith essentially says, since the laws are reversible, then I should be able to get back that glass of wine. It should break, and I should be able to reverse the velocities. Why you reverse the velocities? Because v becomes minus v when you reverse time, which makes sense, right? If you're watching this glass, the pieces are gone, intuitively you would think, okay, if you catch all of them and you send them back with the opposite velocity, they should try to undo themselves. They should try to retrace their path and collect. The part that, of course, Locksmith did not take into account of is you needed to measure. You needed to have the information about the velocity and the position of every molecule that was involved, right? So really the idea when we talk about entropy, you gotta now our understanding of entropy after Jaynes and with now chaos and so on. There is two problems. One problem is that entropy is a measure of the state of the system. It's a measure of what you know about the system. So it's actually the only law that brings in what we know about the system. So if we know everything precisely, we could reverse things. But we don't, and therefore things will just, and because we don't, and the dynamics is non linear. Chaos, so chaos come into play, you make a small error in any of your guesses, you make a small error and they become very large. They grow exponentially. And this was actually came out in a very nice paper about 20 years ago. And in this paper, what this gentleman did, no, it's not him, Matthias Fink, it's the wrong author, sorry. What he did is he did waves and he did particles. So in particles, he has a source here, and these are scatter. So he sends particles and he captures them here. And then he reverses them. When you reverse particle, this is what you get. No organization, right? It's all over the place. Because what he does, he captures the particles, measure their velocity, sending it back, small errors, they can go all over the place. Now he did the same thing with waves. He has a bundle of 2,000 randomly placed bars. And he sends these waves, measure them on the other side, so he sends a pulse. This is what he sees. Again, it looks quite random the way it is here. He time reverses from here and you still get back. So waves are very robust. Essentially, the scale of the wave is so large that it is able to navigate itself. While particles, because of their small size, because of their scale, you could just miss one hit and everything else goes out of the window. So mathematically, what we find is that the perturbation or the errors in waves grow as square root of t. Means as long as we are using this technology for short times, then waves reverse and reverse very really well. With particles, they grow exponentially. So now this brings us to this project. We got a project a few years ago, about 7 million Canadian, to deal with issues on water supply. What are these issues? This is the team, by the way. One of them is, of course, you see Brian Carney there. These water supply lines have a lot of efficiencies and deficiencies. They lose about 30% of their water. One thing that I find in talking to water supply department, they seem to always forget that they lose energy as well, because you have to pump, you have to treat them, you have to put in lots of treatment. So you're not just losing water, you're actually losing all of the other resources that went into it. The World Bank estimates that the monetary value of this money, just direct cost, not indirect cost, is about $25 billion a year. So obviously it is an important problem. So our goal was very simple: try to find a way to save water and energy. What we are against is, why are these systems difficult? And that's why in the title we said underground infrastructure. They are hidden. They are large in scale. They are hidden. They are not accessible. So how can we tell their state when we can't see them? The way we do it now is just does not cut it. It happens at a walking pace. And really the only way around it these days is, I see you're doing quite a bit of a replacement here in Toronto. In Hong Kong, we just finished replacement of 4,000 kilometers of pipes at $20 billion. The estimates are, if China were to follow suit and do similar to us, it will be more than $300 billion, etc. So what we want to do is, can we do it differently? We wanted to do frontier research on waves and their transmission, how we can use it as a diagnostic system, and of course we want to test it, and that's what I'm going to try to show you now. Why waves? Where you look all around you, if you have a system that is not accessible or hidden, the best way to image it is through waves, and everybody has gone through this. All what the doctor is doing, sending waves, getting the echoes. Right? And by getting the reflection, you do the imaging. This is actually now a big project in the US where they're sending waves, and they can send them now and image fishes, or they can image the bathymetry. So they can get it down, just make the frequency high, so they can image to a few centimeters. All right, so what we wanted to do is, why not try to do the same? Why not emulate the same? And what this gentleman is doing here, essentially we want to send the wave. So this is one way of sending a wave, just closing a valve, and these waves will travel in the system at about a kilometer per second. So they can carry and they can bring a lot of information, and Brian mentioned that earlier. Now just 2 pages of a bit of math. So here is the idea. You have some defects, whatever they are. They don't have to be leaks. Any change in the system. The idea is, let's say you send a unit load, what's called the delta function mathematically, a unit load into the system. And what you should get back, it travels and comes back. What you get back, the mathematicians will call Green's function. It's the Green's function of the system, because you send a delta function at this xs as a function of time. In civil engineering, you probably know it as a unit hydrograph in hydrology, or you know it as a unit load method. You know, you put one load and you look at the response and so on. That's really all it is. So it's essentially for one unit, how does the system respond? That's what we're doing. We take this and we flip it in time. So that's all we do, is flip it in time. So really mathematically, we just switch t to minus t, and that becomes our source. Remember, we send it back into the system and see what happens to it. So when you send it back, you're going to send it back through the same system, right? You have the Green's function. What all you do is the convolution integral of what now you reversed with the Green's function of the system. Mathematically, you could write it as this integral. One thing very interesting is, when does this reach its maximum? It reaches its maximum when t is 0, right? You have an inner product of 2 functions. It's maximum when the 2 functions are identical, or one is a linear combination of the other. So it's when t is 0. it refocuses back at its origin. Remember, we put a delta function t, so the source at 0, it refocuses back only at 0 and at the location xs. Now later, of course, when you collect real signal, the real signal has randomness in it. So there is a stochasticity. So if you interpret this in a stochastic manner, then this is nothing but your autocorrelation. Okay? So you could view it from the angle of being the autocorrelation of the signal. So what does it really mean for a leak, for example? All this is all what we are doing. If you send a source, say there is a leak somewhere there, and you're measuring here. We send a delta function, you measure there. What are you going to get? You're going to get a reflection, right? So now what you're going to do is time reverse that and send it back. As you send it back, it can only, if things are correct, can only converge back at its location at time 0, right? It's not going to converge there or there, right? It's at time 0. That's where it's going to refocus. So now, often, of course, when we do the math, we try to do this in the frequency domain simply because convolution become products. So if you remember a bit your math, in time domain, frequency domain, convolution become products, so it's easier to deal with. But besides that, so what we end up with is this norm. Remember I showed you that norm? The integral was a norm, and we said we are looking for its maximum. So it becomes really an optimization problem. We're looking for the location of these defects. That's what these... But interestingly, this time reversal, we proved that under a stochastic process, it maximizes the signal-to-noise ratio. So it's actually the best filter. Electrical engineers will like to call it as a filter. So we're looking for these unknown XL. Remember XL here, although it implies leak, but it could be any defect. And that's, we use it because all of them are reflectors. Okay? A blockage is a reflector, leak is a reflector, etc. So here is, we applied this in the lab. So this is one of the typical plots we get from it. So again, we send, there is a leak in there. This is the test rig. And we get back the reflection. That's the signal we get back. And then we run it. We do the time reversal, and we apply it, and you get the peak here. This is the red line is actually where the actual location of the peak, and that's where these function peaks. Now you notice there is these side lobes here. The side lobes is what we saw earlier in that tank. You still had a little bit of ripples. So if you want to suppress this, there are a couple of ways. Measure more, or also part of it comes because of noise. I will show you could also kill this if we do multiple measurements. Okay? So now what happens, how does it, again, work if you guess the leak? Let's say this is the actual leak and you guessed it to be here. You do your time reversal, the wave will hit back. You're waiting what happens at 0. You don't see any energy. The only place it's going to peak is when you stumble and find that point, because anywhere else, your wave is not going to hit back at time t0. Okay, so what is the time? Because I need to know when I should...
Another 15 minutes or so?
Another 15 minutes. Okay. So here is the comparison of what we've done, essentially with time reversal compared to everything else that we've done before or others have done in terms of identifying defects. So within 1 meter, the resolution, if we get it correct within 1 meter, 96% of the time. If it is within 3 meters and so on, it's pretty much 100% of the time. So let me, maybe we do show you how to do 2 leaks, 3 leaks, and so on. The only thing it's the same idea, but there is one important point I like to mention here. Okay. The point is, in practice, you don't know how many defects you have, right? So it's easy when I'm looking for 2. So what we found really useful is here where we could use the likelihood function. So what we do is we start to search initially with 1 defect, right? And then we do 2 defects, and we plot the likelihood function until it flattens off. When it flattens off, it means you are about there. And we find it all our tests, whether it's in the field or in the lab, found that this is the most robust of actually telling us what the number of leaks are by plotting essentially what we learned as the likelihood function, which we've done in second year. So nothing really fancy, but it's very important because this is always the case that comes in is how do you know? How do you know how many do you have? So we've done this also for more complicated system. Now what I'll show you, there are two modes when we go to the field. So I'm going to show you some problems that we've done in the field. So here there are two modes. You could run it in what's called the active probing. Active probing is when you go and actually probe the system and see what its ills are. Passive is when you are listening. You're sitting there and listening for something to happen. You've got to be there at all time. And a lot these days of actually, there is some consultants going around, and they go to, there is in Hong Kong and Australia, I think it's about 1 million Hong Kong dollars to set for about a few kilometers of pipes, and they're basically collecting all these data at about 250 hertz day in, day out, and they are watching. And I'll show you one of those examples later. Okay, so this is the different modes, and here is the testing field. So the government or the water supplies in Hong Kong has been really kind to us. So this is where we are testing these, and I think it's about 400 or 500 meters long. Brian has been there. So this is where our guys are working. They're trying to set up now for some of our tests that we're going to do for this pipeline system. So we're doing some disinfection there, making sure that it's still water supply. Right? So this is the fire hydrant from where we're going to inject the waves into the system. And of course in this we're going to do a simulated leak. We're going to go to another fire hydrant, open it to simulate a leak and see how well we do in the field. And there is all kinds of connections, as you will see, to the building. So George there is getting it ready. So now this is the simulated leak, so we're going to get some of the water. The question, since this is running, the question we always get is how big of a leak? Really what we found is not how big of a leak. It's the flow divided by the head, which is called the admittance. So the lower the pressure, the easier it is to find a leak. Okay, so this is the signal that we got in the field. So now our guys take it to the lab, and they run it through these time reversal processors that we built. Okay, and to again save some time, I'll show you some of the results here. So this is for October. This is a test we've done in October 2018. Again, we went to this pipeline, injected, measured the pressure at the same location, and this is the output of the time reversal. Let's analyze and see what is happening. We also can plot the sonogram, exactly what you'll see in this medical, essentially telling us location and frequency. So we can bend it. We know which dynamic devices are acting also in the system. So here is what interesting thing is, this is one of the things that we found, right? There must be something there, right? And we didn't know that this was actually happening. So we needed to contact water supply. I said, do you have something here? Oh yeah, we did have a hydrant line. We didn't tell you about it. Why is that important? Yes. If you want us to find a leak that is small, sure enough, we should be able to find a line, right? So this is the leak, of course. You find it there. Here is a connection to customers, and a big connection to quite a few buildings in there. The other one is the other fire hydrant here. And you see this? We knew it was the inlet, but after it was reoccurring all the time, there is a lots of changes. We talked to them. They gave us the maps. They said it's straight pipe in their maps. We went back and said, are you sure it's really straight? They said, well, actually, let's go back. And they dug out, and the map had these windy pipes and all that. So, but I had a meeting with the water supplies and that director. They are more convinced, though. We're glad, because we are actually working with this, telling them, are you sure? And they're saying, well, maybe this is really working. They start to believe it, right? So this is we've done about 6 months later. So we are trying to put this pipeline in a way like you go to a doctor, right? You're going to do regular checkups. So here are the checkups we're doing every 6 months to see if there are any changes. So we find pretty much the same thing. Still, the hydrant's still there, didn't go anywhere. Luckily, the leak is still there. Connection is still working. So pretty much the same thing, right? It's quite robust. Well, an interesting happened in August. 6 months later, we measured, and you already can see, hopefully, that things have changed. And so one thing we measured was all the other measurements were at night. This is we've done during the day. So one big drop here. So initially we got really stuck, and we tried to contact them again. And what we found out is that's actually where their pumps gets turned on to fill up the reservoirs on the top. So you're catching a lot of dynamics, and that's why there is these band of frequencies there. The other one, you see things became quite crazy here, right? And the only thing, let's go back. The only thing we could reckon, we knew they had a PRV, but they said they took it, it's no longer being used. So we call them, are you sure you're PRV? Because it seems something acting like a PRV. And again, they checked and so on. They said, oh yeah, we put it online about a month ago. So again, you do actually find all of these. So usually when we start with this, everybody says you guys are looking for leaks. But really in reality, you're actually checking the whole health of the system. So when you do it, and the one thing though, is that the accuracy will be plus or minus 10, 15 meter. Why the accuracy? We cannot do that valve fast enough. Remember, it's the wavelength. The wavelength is the wave speed times your time of closure. Okay, and that limits us, right? There is essential limitation in physics and what we do with this. So here at the end, the way we're working now in this system is to actually map it up. So we're trying to come up with this, if you want to call it technology. Well, hopefully the engineer will get something in front of them telling them what all of the things you can find. We did this as a blind test that Bruno and Silvia sent us from Italy. They tested in Trento, Italy, and they had a leak, send it to us, and we predicted that there was a leak from that time reverse, and indeed within about 7.7 meters in that case we got that. Now here is a case of a passive again when you are listening. So the idea of this passive is that something happens, sends waves, and you happen to be there listening, and you try to use. So time reverse in this case, I showed you already one experiment we've done in the field, is really easy. Just send it back and the waves should find their origin. This is actually a case where Hong Kong bought these consultant. I should not name who they are. They bought all of these high-tech, and every engineer have it in their mobile. They're looking at the pressures going up and down. Every day they notice at 4 o'clock in the afternoon, they see a drop in pressure of about 10 meters at these two locations. What's going on? See, there is a lots of smart system. What I found is that governments in many places, I don't know if it's here, they're investing a lot of money on buying gadgets, but they are not buying the science that is needed to interpret the gadget. And that's what they had. This became a headache for them because they're seeing this, but they don't know what it is. Okay, because these guys are really good with high tech. They are no insult here. They are electrical engineers. They don't do the waves and the hydraulics. So they said, well, you've seen the pressure, right? It drops. Yeah, but what causes it? So anyway, once we talked to them, we kind of run it. And here is what we did. Simply, they gave us these measurements. We run them backwards. And you see these waves are. This is what we run, and boom, we will like to see. That's where they must have started from there, right? That's their source. So now we said, do you have anything here? They said, oh yeah, we have a fire hydrant here. So are you sure nobody's using that fire hydrant? Well then, they did investigate, and they find around 4 o'clock each day, this truck comes in for street sweeping, it fills up and goes. So water supplies department didn't know about it. It's another department that takes away the water, and you do find these things. So we do So as long as you're measuring them, you could find these. Now recently, actually, this is when I've been here, my students are working to automate all of this. So to automate all of this system so that it measures, it essentially runs this and tells you whether there are any problems. So here is a bit of a bit of a video here to show you how the system works. This is our lab system. So they are trying to first automate in the lab, and then we're going to test the same thing. So this is our looped system. And you'll see them, they're going to do one active probing, one essentially passive probing. So this one is the passive. So they open up, you see the pressure drop, and it gets automated. It goes into the computer, and then it uses this time reversal, runs it, and back predicts within about a minute of all of this happening. It tells you what went wrong or where is the likely location. So all this is being filmed at kind of real time as it's happening, and you see it drops here. So in fact, it was within about, I think, 3 meters from where the real burst is. Okay, sorry. And I'll skip through that. The other one is the active. So again, they were all within a couple of meters. Why within I keep going back to this diffraction limit. So let's look slightly more. The wavelength is wave speed times period, or wave speed divided by frequency. So if you are an ultrasound, when you go to radiology, they are using this frequency from 2 to 15 megahertz. That gives them imaging between a fraction of a millimeter to a few millimeters. Us with valves, if you are really fast enough and do it with mechanical devices, we might get within 10 meters if we are doing really, really good. Otherwise, it's going to be much, much longer than. That's really the limit. You cannot aspire to image better than this. Okay, so that's the limit you can get. So the only way to increase that is to go to higher frequency. And that's what we've been testing recently. That's why we're looking at these 20 to 150 kilohertz. It actually brings the accuracy to the order of centimeters. So here is again our test lab for this. Okay, first I'll show you some of these experiments. These are the different modes. So now at about, for example, 40 kilohertz, what we see is 3 modes. These are the modes I showed you earlier in the pipe. Some of them go radially and some along, and that's why they separate. So that's how these dispersion curves are. So once you know your frequency, you know exactly which modes you're. We're doing this as well on the pipe wall. So this is what we measure on the pipe wall, and the other one is what we measure in the fluid. So this is for a leak. This is experiments for a leak. The leak is at 2 meters in this case. This is high frequency, and you will see a reflection coming back from the leak. It's actually very, very clear in these high frequency. But the important thing why I'm showing you this is now the size of this lobe is within a fraction of a meter rather than meters, tens of meters. Okay, so that's the resolution you get from it. Then we wanted to look also at blockages or wall thinning. What you see here is actually a piece of bitumen. This is from a real pipeline in Hong Kong that actually got dislodged. So we wanted to see, can these waves find it? Okay? And indeed, this is a reflection you get from it, and this is the localization. The other interesting thing about it is when we run it for different frequencies, it gets thinner and thinner. In fact, when we do it non-dimensional, all the curves collapse. So indeed, the wavelength is the important length scale here. I'll finish out by mentioning, you probably are always thinking damping. What happened? Damping does not prevent time reversal of waves. But what it does with damping, eats away your high frequencies. But what you want is the high frequency. So you get a blurred kind of image because of damping. So how can you get back your high frequency? Well, we played with this, just starting with a spring. This is a damped spring, and this is its solution. This is a solution of an undamped spring. You could actually mathematically map the two. Easy to map a damped into an undamped solution. By looking at these phases, I can match the two phases of this and solve for what is the T that I could match the two. we could match the amplitude. So essentially what we could do is have a relationship between the damped and undamped. So what it really means is this is the undamped. What you measure is, of course, the damped. So if you want the damped at time, you just need to look at what you measure at slightly different time, at an early or later time, and you need to shift the phase. You see here, there is one problem. It's plus, it's exponential plus, and there is a time. So essentially, we're trying to put back the energy, right? Dampen takes away the energy. This is trying to compensate for the energy. The trouble with that, when we did it in the lab, is it does not just put back energy into the signal, it also puts back energy into the noise. So you need some regularization and so on. So in principle, under ideal case, and I'm going to show you, here is for a pipeline. This is for viscoelastic pipeline. This is the type of signal you get. And we could derive the mapping between damped and undamped. So we get a nice relationship. It's an integral equation, but it's solvable. This is what you want, the undamped. This is what you measure, the damped one. So in principle, I can find this. And we did that numerically. So you take the damped signal, and I'll show you when we undamp it. And that's what that relationship does. It totally undamps it and brings back all the frequency. So again, it looks though really nice numerically, but when we do this with experiments, we need to cut it off to about here, because otherwise the noise just blows up. But fortunately for us, all we need for imaging is the first wave, because all you need is the wave to hit whatever anomaly and come back. You don't need many wave cycles. So what you get later is not really that useful for you. So again, here is the type of imaging we did with it. These are some experimental work. So suddenly, we actually get some good shape for blockages, right? Let me conclude here. What we've shown in this is that time reversal of waves do and quite robust for viscoelastic pipe. The technique is quite promising. It has high resolution. It's noise tolerant. What it really does, it suppresses the noise. It basically maximizes the signal to noise ratio. It's robust, unlike particles. It's tolerant to modeling uncertainty. And this is why it's the workhorse for people in ocean acoustics, for people in medical devices, and so on. So it can tolerate quite a bit of uncertainty in modeling. There is a lot of tools. There's a lot of tools that are already available for this. If high frequency waves brings down from tens of meters to a fraction of meters. Another thing that actually I didn't mention anything about, but it was a good surprise to us. We were really worried about viscoelastic, because you've seen all these waves, 3D waves and so on. We said, now, if you add in viscoelasticity, it's going to kill us. What we found is that viscoelastic pipes become elastic at high frequency. The viscosity just does not wake up. It takes a long time. It's a much longer time scale than the waves. These waves will do this, finish its job, and the viscous part has still not woken up. So a lot of, and then of course, after you know that, you go back to the literature in physics and you find that somebody has already done quite a bit of work in theory and shown that indeed, viscoelastic, initially it grows with the frequency, but later on it actually decays. All right, well, thank you.